Okay, so before we move on to optimizations, as we discussed, we'll be talking about what are some iterative changes that you need to do into codes to make them like go from recursive to iterative. Okay, so these were two problems that were already there on the practice sheet, like the external practice sheet from the first session itself. So I hope like at least you have seen the questions, if not implemented them. Okay, so this is the very standard knapsack one, and this was the second version that was there, which is the shift of that knapsack version into different form. Okay, now in this particular, like we have discussed this particular problem with the states of TP of I comma what is the weight, right? And from that, for every item we had two choices, that either you take that particular item or you don't take that, right? This second problem, if you have solved it, this is a version where the weights are very high, but the values or the profits that are given for every item is small. So on the worst case, the value summation across all items can go only up to 10 to the power 5, because there are around 10 to the power 3 for every item. And if you take all items, it can be at most vi into n, that is 10 to the power 5, right? So in this particular thing, you need to change the states a bit. So we'll be talking about that. Okay. So first, let's come to this particular problem. In this one, you know that you have a recursion like dp of I comma what is the weight. Okay, and this is the maximum profit you can make with this particular configuration, that you have taken the first I items, you have decided for the first I items, and the rest of the next items are left to decide, and you have already taken a weight of exact w. So what is the maximum profit you can create? Okay, okay, so it's all about what do you decide for each state. Like you can change the meaning if you want to. If you can also take that I have taken less than equal to w weight, then what's the best you can do? Okay, so if we just want to look into how do we implement this particular problem in an iterative fashion, so we'll be taking a look at one of the codes. So I'll be explaining the code quickly. Let me take this up on a separate subline. Okay. So this is the same problem with just an iterative implementation. So we'll be understanding what this iterative implementation is doing. Before we go into the iterative part, these rep means loop from 0 to n, and for means loop to I to n minus 1. Okay, that's the quick go through into the template. Okay. Now there is n and w given to you in the problem. So I'm explaining the iterative part. It's more or less same as the recursive one. It's just that once you learn the iterative one, for some problems it's better to go into the iterative style of implementation. Why? Because either it's easier to code. Okay, as you can see in this particular part, it's more or less same. Like it does not take much of extra effort over there. But in some problems, you might see that okay, iterative one is the only way in which you can solve that particular problem. By only, I mean like the recursive one will take a lot of more effort to implement. Okay, so some of those type of problems we'll be taking up today. Okay, so let's say this is the same recursion. So over here we say that okay, with 0 items taken and 0 weights, the profit that we can make is 0. Rest everything in the table or knapsack table is like minus infinity, that you can make a profit of minus infinity. Now this is something that I personally use, that I generally have a modulo in defined, which is something like 10 to the power 9, and if I take a mod into mod, that is around 10 to the power 18, right, which is pretty much large for this number, because at most the profit can go up to 10 to the power 12, 10 to the power 11 in this case. So if I take it like a minus 10 to the power 9, it will always remain negative. Okay, this is what you can use. Also you can define a infinity, minus infinity, something like that. Okay. Now a knapsack of 0, 0 is 0 profit. Then from for 0th item to n minus 1, I'm looping from 0 to n minus 1 over here, and this is for every different weight that is possible. If I can make that weight, so if it's greater than minus mod into mod, that means that there is some possible way to reach that state, right? So if that is reachable, then what we can do is we can either not take anything for this particular item, so we will reach the I plus 1th state with the same weight, and this is one of the possible profits that I can create, right? So this is one, I will just remax it. So by remax, I mean to say make this either the same what it was earlier, or make it an update to this particular value if it's larger, right? So take the max of out of the two. Okay. Also, if I have made a weight of W till now, and if I'm taking the ith item, okay, if I can take it and the weight is not yet W, I can take that. So I can reach this particular state that I have taken up to I plus 1th item, and I have taken a total weight of J that was earlier till this ith one, and including the Wi, right? This particular state can have a profit which is equal to this. Okay. So just make it a max of that. Like this has a potential value which is equal to max of its own old value, whatever it was from other states, or this particular transition that we are taken right now, that from this I plus J, we get a profit of Vi, right? That is the value at this. Okay. And then at the end, we loop from 0 to W. And for each of the W, we say that, okay, I can make that, if I can make that W, what is the maximum that I can take? Just take the max out of all, and that's going to be your profit, right? That's going to be your best profit. Is this iterative code making sense to everyone? Because in this one, let me explain what this particular part will do. So we are having some sort of table, okay, that we are trying to fill up. When we are at some particular I and on some particular weight, from over here, we say that, okay, I am not going to take the ith item, okay. So this is a 0 index. That's why it's I plus 1 over here. This is this I and I plus 1 is something like an implementation detail, but the idea is you are at the ith item, okay, and you have a current taken weight of W, okay, and you have not yet decided for the ith item. Like it's up to I minus 1 that you have decided, and for ith item you have to decide. So for this item, I can either take it, or I can either not take it, or I can take it. I will reach some W plus given weight of ith item, right? The current W plus weight of item. Okay. So these are the two states that I can reach in the table. Okay. Anyways, when we were implementing the recursion, okay, recursion of I comma W, we were going to fill up this into the table, right? We had a 2D array in which we were filling up the values. So instead of filling up the values through a recursion or a function, what we are now doing is we are just calculating that table itself, because that table was going to give us the value anyways, right? And from a particular state, I comma W, I can either add it, I can not take it, or I can take it. So these are the two states. Now this is something called a forward implementation. Okay. What I mean to say is from I comma W, I am adding its contribution to I plus 1th state and whatever W I can go to, right? This is something called forward implementation. There is another implementation possible for the same type of problems. Let me explain that. So in that, this is called backward implementation. Okay. So in that, we will say that, okay, I have to decide for I comma W. So this I can create by either not taking anything in the previous step, or I can create this by taking something in the previous step. Okay. Make sense? Sorry, W of I. Okay. So if at the ith step I'm going to take Wi, so in the last step my weight should have been equal to W minus Wi, right? And if I'm not taking the ith item, then my previous steps weight should have been W. Okay. So these are the two types of implementation that you can use in iterative style. It is completely based upon you, like whichever you want to use. It's just transforming the same recurrence relation into a loop which you are filling up in the like loops that are filling up the matrix which were earlier filled up by the recursion function. Okay. So based on whichever like implementation you go on to, like either this one or the one that we discussed just now, okay, this one, you will see that, okay, this particular value fills up only values towards down or towards right, or in this particular one, this particular cell needs something from its previous row or somewhere over here. Okay. So this helps us to decide what is the order in which we should fill the values in the DP table, because if we go ahead and fill up in this fashion, what we see that, okay, once we are done with the I minus 1 level, then only we are going to the ith level. And when we reach this particular state to calculate its value, we have already these values and these values calculated. So we can get this particular value using these two values, right? Yeah. Similarly, for the forward implementation, we will go ahead and like loop from like the first row, second row, and so on. We will reach this, add its contribution to this. Okay. So we know that this particular cell needs a contribution from somewhere over here or somewhere over here, right? So when we will reach this particular state, this particular position, we have already got all the contributions that it needs to get the correct value, and then we know that this is correct, so we will add its contribution to whatever state it's going to, right? So these are two different implementation styles. You can pick up any one that suits you well. Okay. For most of the counting problems or min max problems, I generally go with forward style because it's easier to think that, okay, I'm just doing a max or min on at a particular state. But it's okay, like even if you go with this particular style, that you calculate the value using the previous states. Okay. So this is just an implementation detail. That's nothing you should be worried about. Okay. So is this all iterative style making sense, that what we are writing in this iterative code? Can I have some questions on like which part is not directly clear? So here we have discussed a lot of different things like this forward and backward. So this will come up when you start implementing things in an iterative style. So the next task would be to implement the same question in an iterative style so that you understand what iterative implementation means. Like how do you think about in terms of iterative implementation? It's more or less the same. Like it's the same recurrence that you need to code with just array elements, 2D array elements. Okay. Is this clear to everyone? Can I have a quick +1 if it's clear, or if you have no questions, then chat. So sometimes in 1D DP, like when you, so if you remember the problem that we took up in the previous session towards the like start, that what is the shortest path to this particular state, it's very easy to write it in an iterative fashion. It's like it's more like cumbersome if you go ahead and write a recursive function. Like it's more or less same, but still iterative one comes much more naturally in those problems. Okay. Also in knapsack you can code both because it's more or less this equal effort on both the sides. Okay. So quickly discussing what the iterative style is. So you basically are having a array, okay, and we will decide on some order of looping. Like in this particular case, we are looping in this particular fashion, okay. And when you reach a particular cell, that's some dp of I comma j, some I comma j, okay. So I will calculate its value. How do I calculate its value? I know that dp of I comma j, I have some recurrence, right? In a general problem, I will decide on some recurrence. So based on whatever the recurrence is, I will calculate its value. And this loop of order, like loop order that we decide, should be such that for this particular state, whatever things are required, like whatever states from which this particular thing is taking either summation or max or min, whatever it's taking up, okay, all those states should have already been calculated before. Okay, makes sense, right? Is this clear to everyone that if you're trying to do within an iterative fashion, if at a particular state we want to calculate its value, all these values should have already been calculated from where we are taking some contribution at this, right? So in this particular case, when we're like doing a forward call from a particular state, okay, so that means it is going to get to I plus 1 comma j, and it's going to go to I plus 1 comma j plus wi, okay. So even in forward style, if you are at a particular state, you are giving to this and to this, right? These two states. Now note that when you are coming to some particular value, this must have got some contribution from somewhere over here or somewhere over here, right? Yeah, so coming to that, we can just keep on looping like this, and when we reach the previous state, these two states must have been found out, and at this state we would have just done a forward call at these two, from these two states, right? So this must have got correct value. So that's why we are looping on this particular fashion. Okay, if you decide on looping in this particular order, like in this particular order to calculate the states, that's wrong, because when you're coming to this particular state has not been evaluated. Okay, so this does not have a correct value right now. Okay, is this making sense? I'm coming to that particular 2 and w, but is this all making sense right now? Can I have a quick +1 if everybody is able to understand this? That it's just writing the same recurrence in a 2D array form with this, like just deciding on the looping order and calculating the values correctly. That's it. So I think most of you must have implemented in a backward style in recursive one. So we can go with a backward style implementation in this, right? That just fill this particular cell with the, either you take the last element or you don't take the last element. That's all. Okay. Is this clear to everyone? Can I have a +1 with everyone if this is clear? Because then we'll be moving to the next problem. let's move to the next one. The second problem was a bit different. It's the same problem with a different constraint, right? That you have some sort of like change in the constraints of weight and profits. That okay, profit is up to 10 to the power 3 and weights are up to 10 to the power 9. Okay, so if you have already, I think some of you have already solved this particular problem, but if you think about it, this like keeping a weight in the state is not possible now, because we know that the number of the total time complexity is going to be equal to the number of states multiplied by number of transitions. Okay, average number of transitions, so that's going to be equal to a very large number in this case. So it makes sense to keep the profit into the recurrence. So it's, so earlier we were keeping dp of I comma weight equal to max profit that I can create with this state. Okay, so now in this particular problem we use dp of I comma some particular profit that we are making, which will store what is the minimum weight with which we can create this particular profit. Okay, so earlier we were keeping weight over here and max as a result. Okay, p as a result. Now in this particular problem we are saying that okay, what is the, given a profit, what is the minimum weight in which I can create this particular profit. Okay, this is the dp that I'm trying to create. Okay, now this particular dp will work in this case because p is given up to 10 to the power 5, this is 10 to the power 2, so this is there are 10 to the power 7 states, so that will work. Okay, maximum profit that you can go up to is n into p pi, that is 10 to the power 5. Okay. So with this into consideration, we can simply write the recurrences as like dp of I comma p can be either equal to, like you would have taken from dp of I minus 1 p minus pi, whatever ith p was, minus like this, whatever this particular state needed, whatever the minimum weight needed by this particular state was, plus wi is going to give you the minimum weight needed for this. This is one possible choice. Or from I minus 1, if I already had a p profit, then I can do this at least in that particular same weight. So minimum of these two is the possible weight for this particular state, right? So this is what you can do in this particular problem. If I just quickly go into the implementation, that's more or less the same. That okay, what is the minimum weight needed? So for 0, 0 you need minimum weight 0, and then we loop from 1 to n 0 to 10 to the power 5, and if that particular state is possible, like the weight needed is, in this problem you change the like values. So note that in the earlier problem we were storing the maximum p, so we had minus infinity. So in this we need a minimum value, so we are keeping plus infinity, right? So if it's less than equal to plus infinity, then that means it has got updated. There is some possible weight. So just update either like I plus 1th comma j is also possible. This is a forward style. So either I plus 1th comma j is also possible to be used using dp of I comma j, or I can create I plus 1 with a profit of j plus v of I, and its weight would be equal to nap of whatever the current knapsack weight was, what is the minimum weight plus weight, right? This is possible weight. This is one of the possible weights for this particular state. Okay, so this is again like a forward style of implementation. I personally prefer a forward style of implementation because it's simpler to think, because you are at a particular state, decide on its moves and just add their contributions to the next stage. That's it. And when you come to that state, it will get its correct value. That's how I think about it when I'm implementing it iteratively. Of course, you can switch between recursive and iterative implementation whenever you want to. Okay? Because it's not a different power, that like it's not completely different when you think about the recursions, right? The relations remain the same. Okay? And at the last state, like if at particular state, like any particular state j for a particular profit j, if the minimum required weight is less than or equal to w, then I can make that profit, right? So I will just update it with that particular j. Okay, and whatever the maximum profit that I can create such that the minimum weight required for it is less than or equal to w, that's my answer. Okay. So this particular idea is sometimes common, and this particular idea has a name. It's called rotating the state, or state rotation basically. Okay, so if you think about this problem, this has some sort of like a configuration that I comma p comma w. Can I process the first I elements and create a profit p and a w? This is a Boolean answer, right? This is a Boolean, like, can I reach this state? This is a Boolean, yes or no. So in most of DP problems, what we try to do is we try to remove one state, and whatever we have to do, maximize or minimize, accordingly we keep in at this particular position, okay? Or I can keep this over here, or I can remove this and keep it over here, right? Whatever we want to do. So depending on what has what constraints and all in the problem, you can decide on which one to keep or the like as the answer. Generally the smallest one are kept in the state and the larger one is kept as the answer, right? So this is something called state rotation. Like, this is the standard knapsack state, but you can rotate the states by changing weights and p positions in this, and based on that you can also solve the problem. So this particular optimization idea is something called state rotation, and implementation also is like more or less similar. Like, it's the same recurrence. It's the iterative style allows you to write a forward DP, but even if you write it in a backward style, like we discussed previously, it's still okay. Like, it's more or less it's the same. Okay. Is both of these questions clear to everyone? Can I have like any questions that you have up till this understanding of this? Or if it's completely clear, can I have a quick +1 from everyone? Because then we'll be moving to the next topic, like next subtopic. So these two problems, I think most of you have already implemented. If you have not, like after the session, you should definitely. These are very classical problems, in fact. Okay. So today we'll be talking about few non-classical problems. Okay. So this is one state idea, state rotation. So we'll be quickly summarizing at the end. Let's move to the next problem. So now we'll start with one particular problem, which is like the statement is a bit long, but we'll understand the problem first, and then we will move into thinking about the problem. So first, like, let's move into the statement. Okay. So you are given n values, okay, a1, a2, an. Please pay attention right now. Like, if you don't understand the statement, like a large portion of today's session would be irrelevant to you. So make sure you're understanding this very well. Okay. So there are n elements given to you, a1, a2, a3 up to an. Okay. Now all of them are distinct. Okay. This is given to you. Now you have to find out the number of permutations of this. Okay. Such that it's a bitonic sequence. Okay. Now what is a bitonic sequence? Just a second. It first increases and then decreases. Okay. So basically, let's say if you have some sort of values like 1, 2, 4, 3, this is a bitonic sequence because it's first increasing and then it's decreasing, right? 1, 2, 3, 4 is also bitonic, like it's increasing. Okay. So basically, bitonic sequence has a definition that you have some position in the array such that everything before up to that point is increasing, like the consecutive difference is increasing, not the difference, like the values are increasing, and then after that position it's decreasing. Okay. That's something called a bitonic sequence. Okay. Now with this into place, so first of all, the permutation should be bitonic. Okay. The second constraint on the permutation is once you permute it, a of I, so let me write it this way, abs of a of I, so you're given n, a of I and a of I plus 1, okay, should be less than equal to some particular given value k. So these are the two constraints. Okay. So you are given two different values, two different inputs, n and k, n sized array and a constant k. Okay. Find out the number of permutations of this particular sequence, which is all distinct first of all. Okay. Such that first of all it's bitonic, that means it's first increasing and then decreasing, and secondly the consecutive difference between the elements is less than equal to k. Find out the number of such permutations. Okay. And of course you have some modulo given in the problem, that there is some mod which might not be prime, like it does not depend. find out the count of the number of such permutations, modulo sum on. We would not be taking up any constraints. Let's try to solve this in an open way. If you like try to think about it in terms of constraints, I can just give you this much, that the values AI and K is pretty large. Like K or AI can be up to 10 to the power 9. N can be smaller. Like I don't know what the constraints of N is, so we will try to solve it for the best constraint, of course. Okay. So try to think about this particular problem. This is a very good problem. Okay. So if you have seen the previous session, or if you have attended that, you should be thinking in the terms of what we have been doing in the previous session. That how do we build the, like, first of all, try to build a brute force solution. Like how do we build a brute force solution, and then can we somehow solve it better than the brute? Like what are optimizations that we can do in this particular problem? Okay. So take 1 or 2 minutes, think about this particular problem on your own, because if there is any question on the problem statement, you can ask that. Try to solve this. What is this? What are the different DP states that you can come up? Don't write the answers right away. Like keep it to yourself for 2 minutes, and then I will ask, like, what is the state that you're thinking in direction of, and then we will discuss how to do that. Okay? If you is the question clear to everyone? Can I have a quick +1, because this is very important? Like, can I have a +1 from everyone? Because if this is not question is not clear, then we'll be taking up this for maybe like next 40 minutes. So the whole thing is not going to make sense. Okay, that's a good idea. Okay. So I'm just writing one particular case. Like this is just to give you an idea that what are different possibilities. So I'm giving you 1 more minute of time to think about it. Amisha, also you can think about how will you formulate this. This is more or less a good idea, like a correct direction, but still you will have to formulate this a bit. Like the remaining elements should also follow the condition, right? How do you handle that? So I was just writing this to give you some like maybe some ideas on what are we trying to do. But this is just an example. So there are a lot of different possibilities out there in this. How do we effectively enumerate something? So in this, we were not taking consider like there is no problem of k. So let me give you one hint. First of all, the first line of Amisha's comment is the correct idea that you have to sort the elements first of all, because you have to basically pick elements from these given array and create the sequence, right? In most problems that you will see in which you have to pick up elements from a sequence, like in some order, commute them, starting with the sorted sequence is the best way to go, because anyways that does not matter, right? What is the initial order does not matter, like we can process it in any order we want. So sorting it will help us definitely in this problem, right? I hope you must have got this particular sense by yourself also, that okay, if you're having a random sequence, if you have to pick up the elements and create a permutation out of a random sequence, it's better to create that using a sorted sequence, because both these conditions has some property of sorting in it, like right, that there is something less than equal to k, like difference should be less than equal to k, and then there is this constraint of biturning, which is again some sorted part in. So first idea is like processing sorting is good. Okay. How do we do it beyond this? Uh, Sorry, this should be I. So basically the consecutive elements in this, okay, consecutive elements in this should be less than equal to k. Any ideas? Yep, that's a good observation. Middle idea is middle value, no, not exactly the middle value, right? Like the peak of the element, yeah, the peak of the sequence is going to be the highest value, that's for sure. Okay. So basically there would be some like fill up going on, like there is a n sequence that you have to fill up, and there would be some position where you fill the last value, okay, and then on this side there is all increasing, and on this side it's all decreasing. That's a good observation. Okay. So last element, so the problem, if sorted sequence has not second condition true, then answer is 0. Okay, that's also good, that if sorted sequence does not have yeah, there is a gap. Yeah, if the sorted sequence is not following the second condition, then it's not possible. That's true, because if the sorted sequence not following this, then there is some gap which is greater than equal to k in the elements, right? So you can never cover up that gap, because you will have to place it with this one or something above it somewhere in the sequence, so it's not going to follow it. Okay, now the problem, so this is how you think about it. So this was a good observation that okay, last will be somewhere in the middle, but position of the last element is not fixed in this sequence, right? Like it can be anywhere in this. Instead of thinking about the last element, if we think about the first element, how do we go about it? Like what would be the choices for the first element? Where can the first element lie? Like in the sorted sequence, where can the first element lie? Okay, that's correct. The first element can only lie in the first element or the last element, right? Is everybody clear with this particular observation that the first element has to lie in the first position or the last position? Okay. So this, like the last element had like n choices that you had to place on in this, but the first element has just 2 choices. So it's better to start with the first, like in this particular order, because In that case, it would be helpful. Now, let's say you place the first element over here. What are the, how many choices does the second element has? At most, like right now, 2, right? Yeah. So second element can now go after first one, or it can go to the like other side. Okay. So how do we build? So this is more or less the idea. So how do we build a DP? Like how do we build a recurrence out of this? No, not exactly LRDP. Like, yes, you have to fill up like some sort of LR in this particular sequence, but it's not exactly LRDP. Like uh, LRDP is also like an idea. So in this particular sequence, you are basically iterating on this array, right? So it's not exactly LRDP. In LRDP, you generally have like an array on which you are solving, and in that you take subsequences. Of course, it is some form of LR in this particular array, that's the solution array. So what are the states that you will need? What is the most brute way in which you can simulate this? So there are, what is the recursive things that you need to build the solution? Okay. Let's say, so can I write this kind of recursion that I have taken the first I elements, let's say, okay. What do I need? I need more in the sequence. Like what should I keep more in the recurrence? Any suggestions? It's completely okay. Like this is a very experimental problem, and you can suggest anything. Everything will work more or less. Okay, increasing or decreasing where I character is stored. Uh, okay, so let's start. Like I'm trying to think about in this sense. Like let's say I have placed the first I elements. So let's say the first X elements has been filled and last Y elements has been filled. Okay, something like that. So let's say you have placed first there are X elements in the front and there are Y elements in the front. But okay, so we are trying to fill up, like for every element, we will decide whether it will go to the front or it will go to the end, right? I hope this is making sense. Like this is how we generally take decisions in recurrence, right? For every element, decide where it goes. Okay. Now, one more thing is, like if you are writing a brute force for this, we would have gone for something like this, that what is the sequence, like A1, A3, let's say we placed A3 in the front and then let's say A7. Okay. Something like this is these are the elements in the front, and let's say A2 is over here, A4 is over here, and let's say A6 is at the end. Okay. Something like this is happening. Okay. Is this making sense that we can write a brute force something like this? I'm writing the most brute possible way. Okay. Most brute force way possible. That I have placed I elements right now. Out of them, X went to the first and Y went to the last. Okay. And then the first sequence that like the subsequent, like the X length that I've created in the first part is this. Okay. And the X Y sequence that I've generated in the last part is this, and this is the configuration that I'm currently in. Okay, is this state making sense? Like, is this brute force state making sense to everyone? Now, for the next item, what I will do is I will just quickly go ahead and I will try either I have placed I comma X plus 1 comma Y. Okay, sorry, there's more to fill. Let's say I'm now placing A8 element. Okay, so let's say it can go to either the first part. I've placed it in the first part. Okay, I plus 1, I plus 3, A7, A8, okay, something like this. And the other part remains A2, A6. Okay. This is one particular recurrence in which state in which I can go to. And the other state can be I go to I plus 1, comma X, comma Y plus 1, A1 up to A7 it was there. And then on the last part, I appended A8. Okay. Is this making sense to everyone? Yeah. So that's some optimization that you're talking about. We'll come to that. First, there is a bigger optimization that we need to do. So this is a brute force. Is everybody convinced with this brute force? So for the last element, we will just check that whether it satisfies both the endpoints or not, something like that. Okay. So what we are trying to do is we are writing this brute force and we are like doing this both the transitions, and at the end we will check that whether we are satisfying the second condition. But we can of course do better, right? Like when we are appending a8 at the end of a7, we can just do a check then and there that whether it's possible to append a8 at the end or not, right? That whether like this is followed or not, that a7 minus a8 is like apps of this is less than equal to k. In fact, A8 has to be greater than A7. Like we are following, this is increasing and this is decreasing. Okay. This is the last half and this is the first half. So it has to be in this format, right? So whether this follows or not. Make sense? So we are trying to do both of these, like we will from this particular state try both of them only if like this particular condition holds, right? This we will go to this particular recurrence only if this condition holds. So we are doing some sort of pruning over here, that we don't want to go states where it's already invalid, right? Is brute force, is this brute, so this is all about the brute force. Is this brute force clear to everyone? Can I have a quick plus one? Like in brute force, doing some small optimizations like removing one parameter here and there will not help you like reduce the complexity, because you are iterating on everything possible. Okay. Only when you use DP, then optimizing on state makes sense. Okay. It's just going to be some extra parameter that you are doing a brute force. Okay. So is everybody clear with the brute force? Can I have a quick plus one on the chat? Well, unless you understand the brute force, it's not possible. So now from this brute force, we will go to DP. Okay. So I'm quickly removing these two transitions. Okay. Let's talk about this. So first of all, do we need to store this whole sequence over here? So what do we need out of this whole sequence? Yeah, last element, right? So a better way to write this, which will more or less, which is more suitable for DP kind of problems, is keeping only the last value, right? So we will go to recursion of I comma x comma y, what I comma x comma y, and what was the last value over here, and let's say last value over here. Okay, I'm just writing them in like just two values, L and R. Okay, so I mean to say L is this last value in the left side and R is the last value in the right side. Okay, yeah, the last, not character, it's number, right? Yeah, so this is the state that we will go to. Now this particular, from this particular state there is one problem. We cannot still memorize this. There are like, this can be up to 10 to, this can be up to n, I can be up to n, x can be up to n, y can be up to n, but the values ai individually can be up to 10 to the power 9, right? AIs, I say that AIs will be up to 10 to the power 9. AI is up to 10 to the power 9. So it's not possible to keep AIs in the state, because then this will be equal to less than 10 to the power 9 and then we are doomed. Like it's not possible to save it. So how do we, can we do better than keeping LR in the state? How do we improve on this? We will need to keep LR in the state, that's for sure. But instead of keeping on the value, can we do something better than that? Like, because the values are 10 to the power 9. Yeah, it's distinct, so you can keep the index. Okay. Basically, what I mean to say is this LR we can keep from this particular array that we have a sorted array, right? From this only that L or R value has came, right? So we can say that, okay, this came from, so I can write the recurrence in this form, recurrence of I comma x comma y comma the last value, like the last element of the right of the left above came from, let's say, A index in the sorted array, and this came from B index. Okay, now these value is fixed and this can be up to 10, this can be up to n. Okay, so everything now can only be up to n. So this is something that we can memorize easily, and we can use order n to the power 5 TP in this, because from this particular state there will be just two transitions, that whichever is the next I plus 1th item, either it will append to from this. Let me just quickly explain what we will do. So from this we will have two transitions. Either we will go to recurrence of I plus 1 comma x plus 1. If I'm printing at the front, of course I will check it with a, because a is the last at the element of a. So let me write the recurrence. So if I write I plus 1, okay, I can go to this state like I plus 1, like whatever the ith element was. Let's say I place the ith plus 1st element at this position, and this can be b, okay, or I can go to this particular state. The addition of all these will be the answer, because these are both possible. Okay, these only happen with the two conditions in place, that okay, a minus, sorry, uh, a of I plus 1 minus the initial arr of I plus 1, arr of a, okay, this should have been abs of this should have been equal to less than equal to k, and in this abs of arr of I plus 1 minus arr of b should have been less than equal to k. Then only these two transitions are possible, right? These are the conditions, and if it's possible, then add it to this particular transition. So by that we can get the answer, okay? And we can of course memorize this. So it will take every state will be visited only once. So the number of states that are possible is n to the power 5, and there are just two transitions from every state, right? Is this clear to everybody? Can I have a quick +1? Because this is one checkpoint in this particular problem. In fact, this is checkpoint 2. We have first checkpoint was going to the brute force. Okay. Any questions up to this? I will pause for 1 minute, because you need to digest this first, that how did we go from this particular problem to this, by first of all sorting this, because of course it would be easy to place the sorted ones, then building a recurrence that okay, I will save the first half and the last half that I'm building up, and x and y in the number of elements, and based on that I decided transitions. Now I saw that okay, last element is only what is deciding what to place, so I can drop off everything and just keep the values. Now keeping the value is very difficult. This is a very important observation. It will help you in a lot of problems, that when you have to keep values in the recurrence, but it's difficult to keep the value, so keep the index from which it's coming. So just keep the index in the original array, because n might be small but the value might be large. So from that index you can later on take out the value, right? It's a static array. So this is a very important idea. Okay, so that helps us to reduce it to n to the power 5, where you have just a simple transitions of two type: place at the first, wait at the end. Of course there is one last caveat, that when you're placing the last element in the whole sequence, it has to satisfy for both the sides, but that you can handle separately, right? It's just a recursion, so that will be like a base case at the end. Okay, so this helps us to get a n to the power 5 solution. Now we will try to optimize this even further. Okay, now there is one observation that you can do in this, very easy observation. What is that? How can we reduce the states a bit? Like, can we do some optimization on the states? Okay, that's a valid suggestion. I think someone else also suggested this one before. Yeah, x plus y equal to y. That's always going to hold true, right? Because this I means how many elements you have processed. Okay, x means how many elements were there on the left side, and how many elements have you placed on the right side. Now of course I has to be equal to x plus y, right? Like there are I elements that you have placed and x are there on the left, so I minus x needs to be on y. So you can easily drop off one of the states, because you can later on get that state from the other parameter, right? I think we have discussed this particular idea is called state space reduction. Okay, that you can drop off a state whenever you want. Okay, in case it can be like found out again using the other states that you have kept in the recurrence, right? Is this clear to everybody, that wherever in the recurrence you were using y, just like drop that off, because you can get the value of y inside the function by using this expression that y is equal to I minus x. Is this clear to everyone what we're trying to do? Yeah. Okay, so that will reduce us to, let's quickly write this. recurrence of I comma how many we have placed in the front, okay, in the first side, okay, uh, the A value and the B value, okay, that is the positions of the last and the first, like last and the last of the left side and the last of the right side, okay, indexes. So this is a order. Now the transitions will remain two only. This is the n to the power 4 solution, okay. How do we optimize even further? Any ideas? In fact, in the original problem, like where this idea is inspired from, order n to the power 4 would have been sufficient to pass, but still we will optimize it even further. B can also be calculated. Uh, Before coming to B, I think B can, I think instead of B, I think uh, the better thing that you can think about is to think about this X. Do we need X? I mean, in the recurrence, do you see the use of X anywhere in deciding what we can do and what we cannot do? So this is a bit difficult to digest. I will try to explain this one. But if you want, you can also remove X from this particular state, and you will say that recurrence of I comma A comma B is nothing but the number of sequence such that you have filled some element, you don't know how much, okay. So I'm just changing the definition of recurrence by now. I have, so earlier the definition of recurrence was like what I was storing is the number of uh, ways to fill up first I elements such that X of them goes to the first side, Y of them that we have removed goes to the right side, and the last element of the left side was A and the last element of the right side was B. A and B are indexes, not the value, okay. So from this, we can say that we can drop off X and we can say that, okay, I'm just changing the naming of, like, I'm just renaming my definition of the recurrence that I want to calculate. That my recurrence of I comma A comma B says that I have processed I elements and my whatever there are, like, I don't know what X is, but the end element is ARR of A, okay, and the right element is ARR of B, okay. Now I don't care what my X and Y's are. Why? Because anyways I have to calculate it for all possible different X's, right? Like X does not matter to us. Like only thing that is guiding in the expression to check whether some particular transition is possible or not is the A values on B values, right? Like this was B, A over here. This was B, right? So that is only deciding that whether we can take something or not. So we are just kind of redefining our recurrence such that it's now going to be equal to, when I just say that I don't need X, whatever the length is, I'm just fine with having the last value as A of AR of A and AR of B. I'm basically saying that this is this recurrence, like let's call this recurrence 1 and let's call this recurrence 2. Okay. Recurrence 2 of I comma A comma B is nothing but summation over I equal to, sorry, X equal to 0 to n recurrence 1 of I comma X comma A comma B. So basically what I'm saying is I don't need to decide on how many elements X and Y's are there as long as I know the last elements, because I anyways have to calculate the total number of ways to place all the I elements such that this condition is valid. That I can check using these values. And anyways, I have to take up the summation across all of the ways in which the first increasing sequence is some X and then it's Y. So I have to anyways sum it over all possible X's, right? Like all possible different X's. Like it's just 1 and then over here, 2 and then over here, 3 and then decreases, right? So I have to anyways sum it over all X's. So why not define the recurrence in such a way that I don't even need X and Y in the recurrence? Makes sense? So I'm just defining this recurrence 2, which is my new recurrence, as whatever the recurrence 1 was, this summation over 0 to n. Because anyways, my answer is going to be this particular value. So let's call this. My answer is going to be, earlier my answer would have been equal to recurrence of, I start with a 0th element and my x was 0 initially, and my let me explain that. This would have been -1 and -1. So I'm saying that whenever is -1, I'm saying that it's not yet decided. So this is some sort of extra value that I'm creating. It turns out, no, the complexity would not be same. We have just decreased the complexity right there by dropping x. Let me explain why this is happening. So we don't have to do this summation all over, right? This new recurrence over here, recurrence 2, I comma a comma b, is self-sufficient in itself. Like there is just two transitions possible. Either you place the next element at I plus 1, write this. Either this new I plus 1 element goes to the first part, or it goes to the second part by these two, whatever the conditions are. Okay, I'm not writing the condition. There are two conditions that it should follow. Okay, but this recurrence is self-sufficient in itself by calculating its values from the smaller values, right? So this is the actual power of DP that it allows you to have. Like you have the full liberty to decide that what I need to keep in the parameters and what my recurrence or DP will mean. Okay, whatever you say, if I can create that particular number for this state using smaller instances of itself, then I can use that particular definition. I can save anything. So earlier we were saving how many sequences, such that I have placed I, first was X, then A and B. Now I will say I have placed I and there is A and B. That's it. Anyways, my answer is going to be equal to recurrence 2 of 0 comma -1 comma -1, because this will count everything that is possible. I don't need to count my x's, right? So understand this very well, that you are not bounded by anything to define the recurrence into. Like you can say that my recurrence gives me this value, some random value, something that you don't even know how to calculate. But if you have some recursive relation by which you can combine the values of smaller instances of the same problem into the bigger one, then you can keep that definition into place. Like that's all. So this is basically a big jump. Like earlier the definition was completely else, like what we are calculating in the recurrence. Now we drop off x and we say that we don't even care about x. This will give me the answer directly, that I have processed I elements and my last element is A, like over here it's B, and I need to place some elements over here, rest of the elements over here. Either it will go to this and this. Based on that, whatever the number of sequences, that will give me the total count. Because the reason we could drop off x is never used in any of the relations in guiding what is possible or not, right? Like it is not used over here. So why to keep it in the state? So that's why whenever you are designing DP, keep in mind that your states are designed in this fashion so that some constraint in the problem, like you can take at most x, or the neighboring difference should be less than equal to k, something like this. Your total sum of weight should be less than equal to w. So that are the things that you try to keep in the state, so that those can be kept in check, right? That those are holding true or not. X, nobody cares about x, right? I don't know where my peak element will happen, but that's okay. I don't really know that. I don't really want to know that. It can happen anyway. Over here. I don't really care about that. Just find me the sequence which starts at this and ends at this, and it places all the I elements. That's what I need to know, right? That's the question. So drop off x, that's it. Is this clear to everyone? Can I have a quick +1 if this is clear? So this is basically, I'm now saying that I'm just defining this recurrence. Recurrence of I comma a comma b. Find me the number of sequence by placing the first I elements, and the last element placed was A, and like ARR of A, and of like on this side, okay, I'm placing on two sides. Okay, if this is the whole ground, I'm placing at two sides. Okay, and still I will have choices. So the last element placed over here is ARR of A, and the last element placed over here is ARR of B. Okay, so find out number of such sequences, after number of ways to fill after this. Okay, that's what I'm telling you. So can I have a quick +1 to this particular part, that if this is understood or not from everyone, because this is checkpoint 3. Any doubts up to this? So the checkpoint 3 teaches us that we have the liberty to decide whatever we want, that whatever my recurrence will give me my answer until the point that I can calculate it from the base, from the values. Explain the base cases. So base case is nothing but like I will start from 0 comma -1 comma -1, right? Based on this, I can either go to like something like I have placed one element and the 0th element went to this side and it went to this side, and it will keep following till I reach something like I have to I'm at n-1, and I have, let's say, some a over here and some b over here, okay, and then I have to place the last element, okay, whatever the ARR of n-1 is, I have to place that. So in this particular case, I will just check whether it's satisfying with both of them. And from this particular state, I will return 1 if I can place this safely in between these two elements, or else I will return 0. That's it. So at the last move, just decide what you can do. Like, can you do that or not? If it's not valid, then return 0, or if it's valid, return 1, and everything. Like, we are just counting it, right? It's the summation of two choices. At every place, we are like, this recurrence is sum of these two recurrence. So at every place, it's just sum. So at the end, if you return 1, it will get summed up properly, and you will get the total number of sequences. Let's start. Okay. So this is how you design base cases. Like when the last move is done, or you're about to place the last move, just decide what will be the number of answers or number of things. So whatever the definition of this DP is, like whatever definition of this recurrence is, just satisfy, like just think about the definition and think about this state. What should be my value of by that definition? Okay, based on that, you just return the value. One more thing, if it's counting, it's generally 0 or 1 at the base cases. If it's maximization problem, it's generally -infinity or some 0, something like that on the base case. If it's a minimization problem, it's either positive infinity or some 0 at some cases. Like this is sometimes true, most of the times true. You can think about in this direction, but of course as we discussed, that it's completely up to you what you take in states and what you take in the meaning until you can like recursively build that. So as long as you can build that, it's okay. And with that, we can say that whatever you want, you can keep as the base case. Just think about the definition of the recurrence, and that will give you the base case. Okay. Okay. So now this is our new checkpoint. This is the recurrence in which we are talking about. Can we? So this is order n cube. Okay. This is an order n cube DP because okay, this is an order n cube DP. Because there are n cube states, and from every state we can do two operations, right? Either place it at the front or place it at the end. Can we optimize it even further? So this next optimization can be like observed from these two transitions that is possible. This should be equal to I. So where we place the ith element, right? The previous element. This is the recurrence, and this is the transitions. Can we optimize this even further? Any ideas? Let me give you one more hint. That's the hint. That when you are at I plus 1, something is happening, that you always have I at one of the twos. So is all distinct a comma b reachable? I think no. One of them has to be I, right? So can we do some optimization based on that? Like whenever we reach a state with some I plus 1, one of the other two values has to be equal to I for sure. So can we optimize on that? So it turns out we can. So we just need to redefine it a bit. So whenever you are reaching some state, like even from start to any place, okay, and whenever you are at some recurrence, okay, I comma a comma b, we know that either a is equal to I minus 1 or b is equal to I minus 1, right? This is always true. Is this making sense to everyone? That whenever we reach some state, some state like this, whichever is reachable, either a has to be equal to I minus 1 or b has to be equal to I minus 1, because we are processing the elements in a sorted order, right? So the last element must have been placed, the last element I minus 1, when you are processing the ith element, the I minus 1th element has been put either towards at the last over here or at the last over here, right? So one of them has to be I minus 1 for sure at every valid possible configuration. Is this clear to everyone? Can I have a quick +1, because this is an important observation. Okay, so once this is understood, the final optimization is possible now, that we can say that I will say recurrence of I comma some b comma 0 means, so I will keep like something like 2 over here, which can take either 0 or 1. What does that mean? So I will say I can reach this state I comma some a comma 0, which means my state is something like this, that I have built some values over here and some values over here from front to an end, and the I minus 1th value was over here, and a was the index of the last element over here. Okay, and if I reach something like this, rec of I comma a comma 0, sorry 1, which means that I have this particular space, I have filled this, I have filled this, this is equal to I minus 1, okay, and this is equal to a. Okay, so we have to save two values, right? One for the one end and one for the other end, and we can append at any one of those two. So we will keep a track of 0, like using a 2 value state rather than having a full a, that which one of the two was I minus 1, and the other one has to be the other value that is present in the state, right? So from this particular flag and a and I can calculate the value of b, right? What was the value of the other state, right? Like what I mean to say is, given these three values, I can easily uniquely find out the values of a and b of the previous recurrence, right? I can easily find out the value of rec of a comma I comma a comma b. What was the value? So if it is 0, then I know that a is equal. So that means that this recurrence, let's say this is recurrence 2, this was equal to recurrence of I comma I minus 1 comma a, and this was equal to rec of I comma b comma I minus 1, because we know that one of them has to be equal to I minus 1 for sure. Sorry, this is a, right? So we can drop off one of the states and just keep a 2 instead of that state by noting that, okay, which one is I minus 1. So why to keep like a space where there is n different possible values? We know that one of them has to be equal to I minus 1, so we can just keep a 0 or 1. Okay. So now with this, we have a final state that is possible, that we can solve this problem in the recurrence of I. What is the value of one side, and the other is equal to, which one is I minus 1, okay, and the other value. And this is like, there is 2 possible values, this is n possible values, this is n possible values. So this is an order n square transition, order n square state, and there are 2 possible transitions at each place. Is this making sense to everyone? Can I have a +2 in this case if it's clear? Okay, so everybody's attentive, that's great. Okay, so this was a difficult example, of course, like nobody expects you to go from this far, like go this far in an actual problem. This is a comparatively harder problem, but the thing is, this one problem illustrates a lot of different ideas that we talked about. Okay, so we will quickly go back into checkpoints. Okay, this was checkpoint 4, and we will see what are different optimizations that we talked about, because this one problem talks about a lot of different optimizations that are possible in a like individually in a lot of different problems. Okay, so you don't need to understand this whole problem as such. You need to pick up the optimization ideas that we use in this particular problem and use them in different problems. Okay, makes sense. So now in this particular state, we started with the brute force recursion. Just a quick recap. Okay, I will be going fast this time. So brute force with the sequences in place, checking this particular condition that when you place. Okay, now in the sequence we saw that we don't need, this is how we generate from brute force to DP, that we don't need the full sequence, we need just the last value. So keeping that last value into the recurrence. Now keeping the value itself is difficult. This is like there is a big optimization over here. This is something that you need to understand, that whenever you need to keep the value, instead of value, keep the index. That reduces complexity to n, because n is mostly bounded. Values are generally unbounded, very large. Okay, so that gives us a possible solution, but not yet optimal, with a recurrence, and that has two different transitions. Okay, now from this transitions, we did a state space reduction, which means that whenever you have like redundant states in place, you can drop them off and recover them using the other values. Okay, so I, x, and y. So y is equal to I minus x, so we can get that back. So we can just drop off that. Okay, so that now reduces to n to the power 4, because number of states into number of transitions is n to the power 4 into 1, order 1, 2 transitions only, right? Now from this state, we say that okay, this state is okay, but rather I would like to redefine my recurrence by dropping off this k, this x, because I don't really care where my x, like I don't need to check x anywhere, even at the base case or even at anywhere in the middle. So that does not even govern my any operation. So why to keep that in state? So just drop them off and redefine my recurrence, that I don't even need to x, I just need some sequence which goes from this A and B, and it follows some bitonic sequence. Anyways, like the way we are generating it, it will follow bitonic by sure. Like the way we are generating it, it is like guaranteed to be bitonic, because it's distinct and we are increasing and increasing on both sides. So it's going to be bitonic for sure. Okay. And we are also checking the condition by placing every element. So we can redefine it into recurrence 2. And that gives us a very nice order n cube solution. Okay. Now this n cube can also be optimized by looking into the recurrence, that okay, from any particular state, whenever we are doing a move, at least one of the state is always I, because the last element has to be put in one of them, right? So why to keep A and B? Rather, we can reduce the state a bit and we can keep like which one of them is I and the other one is some other value. Okay. So from this, we can say that I can keep dp of I comma a comma 2 or b comma 2, which means like this new recurrence I comma a comma 0 means I have placed like a at the, so 0 means like I minus 1 was placed in the front side, so I minus 1 is over here and a is at the end, or the other one is either a is over here or I minus 1 is over here, right? So this can give, this gives us, this retains the full information that is needed, and these are the only type of states that we will ever visit. We don't even need all possible a and b combinations in the states, right? Because every time one of them is guaranteed to be I minus 1, the way we are filling it. Okay, so this gives us like a state where n and 2 is there, and there are n squared states, order 1 transition, that's order n squared solution for this. Okay, is this clear to everyone? A +1 this time, finally. So that's all for this particular problem. Can I have a quick +1? I think some of you are missing. Any doubts on any part of this? Okay, fine. So we discussed a lot of different optimization ideas. We are not going into implementing this, so but keep these small ideas in mind when you are implementing, when you're thinking about a new DB problem, because it might just one part of this, like this last part, maybe like keeping a 0 1 instead of the value, or dropping off some value, or something like state space reduction, or designing the state, like these individually can be used in a separate DB problem. Okay, now this problem covers all of them in one go, right? Okay, so this was the major problem that we would have to tackle in today's session. Now let's talk about another problem. So this time we will try to tackle this particular one. So these are individual ideas that you can use in different problems. Again, like you don't need to use all of them, but individually, each of them is very relevant. So this new problem is you are given an you you have to create an n-sized array. Okay, like you have to create an n-sized array such that each of the element you know L of I and R of I. Okay, so you have to fit. You don't know the value of A of I, but A of I has to be between this range. Okay, makes sense. So you have to you have to find the number of such arrays possible such that for each of the positions you know Li and Ri, and the array that you create should satisfy the condition that are given in each position, and the sum of the array is less than is equal to x. Let's say, let's talk about equal to x. So find out the number of arrays that are possible. Okay, you are given initially n and L of 1 to L of n, R of 1 to R of n. Find out the number of arrays such that each of the AI's values follow this particular constraint for each of the positions, and the sum of the array is equal to some given value x. Let me, okay, so no bounds on constraints yet, but I can give you this much, that Li and Ri can be, okay, let's start with some constraints. I think constraints will help you decide the problem. Let's say n x Li Ri in this case is up to, let's take 100. Anyways, that is not going to help. Let's take 500. Sorry, let's take 500. So find out the number of arrays possible, modulo some mod. Okay. Think about this. No solutions directly on the chat right now. Like maybe after 2 minutes, you can keep written and paste that right down. But let everybody think about it for maybe 1 or 2 minutes, and then we will talk about the solution. This is like fairly easier than the previous problem, so don't go by judge by the like difficulty of problems. This is more or less, you can think about, is some standard problem that you already know. Okay, so think about it on your own for 1 or 2 minutes, and then we will take this up again. Okay, if you have any, like, is the question clear to everyone? Can I have a quick +1 on that? Because again, if this is not making sense, question is not making sense, then the rest of the things will not make sense. Okay, if you have any doubt on the question, you can ask, or take 2 minutes and think about how do you solve this particular problem. And I think by the amount of practice, if you have done fair amount of, like, at least 50% of the questions that are given on the platform of DP, you should be able to solve this for this particular constraint. Okay. So the inputs are n, x, Li and Ri. Okay, like all Li's and Ri's. Okay, so any ideas? What can be the state for this problem? Okay. Yeah, so that's the recursive idea. So like when you're you have to take I, that which index you are choosing right now, and of course you need to take elements in Li to Ri. That's true. We can do it for less than equal to x. That's possible, but like that is not going to help us in this problem. Like uh, you can think in that direction, but again, like how do you even solve it for less than equal to x? That's equally challenging problem in this case. So can you relate this to some problem that you have already solved? In fact, we have solved that in today's session itself. So we have solved that problem in today's session itself. What is like one, yeah, knapsack. So isn't it somewhat like you have to create a knapsack of weight x, exactly weight x, of with n elements, and each of the element can be from Li to Ri. That's the only change, right? So can we try to design something, some recurrence in that format itself? So think about the recursion first. Like how do you design a brute force recursion in this case? First of all, that is important. How do you write a brute force recursion? So can we write something like that? That okay, let's say I am writing a recursion that I need to process the ith element. Until now I have taken, let's say, something like a1, a2, a3 up to ai minus 1. These are the values that I have taken, and this is the recurrence that I will keep. And at the ith element, I will maybe loop, because anyways li and ri are up to 500. So I will loop for all different values of a of I, and I will append it at the end, and I can go to recurrence of I plus 1 bracket a1, a2, a3 up to a of I, whatever value I choose, a of I. Okay, a of I in belongs to li to ri. Can we not write something like this? Is this recurrence clear to everyone? Can I have a quick +1, because this is important? So every time you have any problem like this, think in terms of recursion first. That how do I like write a recurrence where I'm deciding on the element right now? Okay. And in this case, you just pay a big quick attention that okay, li and ri are small. That's why it's given in the constraint, right? So we can just simply use all possible values at a particular position. So what do we write as the DP now? Like, can somebody quickly tell what can be DP? Yeah, so we can take the sum, right? So anyways, this sum, like even in knapsack, like keeping the whole track, like keeping the track of all elements previous does not make sense. So we can just keep the sum. So let's say recurrence of I comma sum means that I have decided the first elements, and then I have to decide from I to the rest of the elements. So how many ways are there? So I can put ith element as like for all different a of I belonging to li to ri. Okay, I can go to recurrence of, like it's a summation over all such recurrence, like all possible ways to create I plus 1 comma sum plus a of I. Is this clear to all? Like when you're counting, you do a summation. When you're taking a max, you take a max. That's it, right? Is this clear to everyone? Can I click +1? Because that's the whole thing. Like that's all in this problem. Right? Now we will talk about few things that you can do to this particular problem. Let's say the first change that I do is I just remove li and ri from this constraint. Now li and ri can be any value. How do I solve this again now? Let's say li and ri can be up to 10 to the power 9. How do we solve it now? Uh, yeah, you can do that. Also, like a sum left would be always be less or equal to 500. That's what we are saying. Sort of. Okay. In fact, you don't even need to change the reference anything. Like just don't consider anything more than 500. Like make li equal to minimum of li comma 500, ri equal to minimum of ri comma 500. Like make this 501. So you don't even need to consider anything more than 500. Make this min of 501 and make this up to 500. Why 501? Because if it was more than 500, then no possible value, right? That's why. Okay. Is this clear to everyone? This is a quick observation. So a lot of times problem setter try to trick you by giving these kind of constraints into place that is not even relevant. Like it's not ever going to be used in the problem. But you just have to like you just don't need to get started by looking at that and just understand, okay, there is something that is there that is that is always working, and you just have to change the constraints on your own. So be careful about these quick changes that a lot of setter do. Okay. Now let's talk about this particular problem with the type change. This is 5,000 now. Okay. Now, anyways, we have already discussed that li and ri don't matter, right? Like even with a higher constraint, you can make it to 5,000. Okay. So now we will solve this for li and ri are also in this same bracket. Okay. And it's up to 5,000. So how do we solve this then? Think about this for 1 minute. Like, of course, like this is our base part that on which we will be building. So think about from this particular recursion that okay, this was nothing but order n square states and order n recurrence, right? So what can we optimize in this? Like what can we reduce in this? What is there anything that we can reduce? Think about this for 1 minute because this is difficult but still possible. You can think about what is out of these two, what can we reduce? Like either you do an optimization on state or you do an optimization on transition, or like if in state you have to remove something or like take something better, or if you're doing it on transitions, you need to calculate things much faster, like rather than looping on all possible values, do something else. So what can we do and how? Think about it. Binary search is not going to help. Like it's we have to loop on all possible values of AI, but because like we have to count the number of solutions, right? We are counting the number of solutions, so it's not like we are finding some optimal or something like that. So binary search helps us in a lot of uh, maximization and minimization problem, as we have discussed. It's not really helpful over here. So it's some technique like binary search that we have already discussed that is going to help us in this problem. Not like I'm not saying like, I'm saying something that you already know. Okay. So let's try to write this recurrence in iterative format and see that if we can see something in the into happening in that place. Okay. So we are using this recurrence only. We are just writing it in an iterative fashion. So when we will write it in an iterative fashion, what will happen? What will end up happening is you have some rows, right? And at this particular position, you have like, so we are just basically calculating from the next states, right? Which are states I can go to next. So when you are calculating this particular value, some I comma sum, okay, so that means that needs you to calculate some value from over here, like I plus 1 comma some sum plus ai. So it needs something like this from this particular value, right? So how will we iterate on the values to calculate this efficiently? Like when we, what will be our loops of iteration? Like how will we calculate this particular dp in iterative fashion? We will have to go in this fashion, that we go from down towards this. Because then only when we reach this particular position, the values of all these things that are needed is already ready, so we can just get the summation by looping, right? Now can you like think about some optimization from this diagram, like using this, think about this and this diagram. So we are looping and we are trying to find out the dp value. So understand, keep in mind that you are doing it in an iterative fashion. Is there something that looks like is possible? So we are calculating this. This is going to be, let's say this is sum plus li. Okay. So we need this particular value. We need this value. We need this value. We need this value up to sum plus ri, and we need the sum of these values, sum of these positions. Yeah, we loop up to valid states. Okay, that's possible, but valid states can be order n. That's not going to help us. Like everything is going to be valid more or less. Last AI choose. No, I don't think last AI is going to help us, because this sum is needed for us for sure. Okay, and I, this is an abstract type, but we need to, so this transition is nothing but getting the sum of these values over here. Yeah, you need to use a prefix sum. Okay, that's the whole idea. So when you are solving this, so the idea would be solve this for a layer, okay, and then compute a prefix sum for that layer. Okay, then when you are solving for the next layer, you know that you are going to need some range sum in the next layer, right? So use the prefix sum to calculate that in order 1. So this summation can be found in order 1 now. Okay, and then we can get the value for any state in order, and like there are order 1 and the total time taken would be order n square. Repeating on what I said, when you are calculating this kind of like recurrence, that you know that this particular state depends on continuous values of some previous row, or depends on, let's say, minimum or maximum or sum of some continuous value in the previous row. You can optimize, you can calculate that value very fast in previous row by doing some pre-computation on the previous row, right? You can create a prefix sum on the previous row. Okay, and then when you need for this, you know the range, right? You can of course like put in these values and find out like some l and r that you need in this range, right? Some sum plus li, sum plus ri, take minimum with n and other things, like so that you don't go outside the bounds and other things, but you can get some l and r bound on this row, right? So you just need the sum, like we basically need the sum of recurrence of I plus 1 comma some l, some I equal to l to r. So that is a very standard position. Like since you know all these values, you can pre-compute a prefix sum and calculate this dp value using a prefix sum over this layer, right? Is this all making sense what we are talking about right now? Can I click +1 if this is making sense? Okay, And that's the whole idea. That will allow us to solve this in order n square total. Okay. So should we code this particular problem? Okay. So I think let's move into implementing this so that I can show you one like maybe quick live implementation on the iterative part, and how do you also like inculcate this prefix sum idea into code. I think it's doable, but still let's look into this. Let's stop. So I designed my states in this fashion, right? That I need the next layer sum of this plus this. So I will need to, let's say I need n L of n R of n. Okay. Okay, that's the whole input. Now we need to calculate the DP value. So in this case, we can create an integer DP. Okay. So I will not be taking care of modulo. That you can take care when you are implementing it for the original problem. But this is something that we're just taking a summation right first. We need to take care of long and things. That's completely implementation based. So when we need this particular value, when we calculate some I comma sum, we need to know its next layer's value, right? So we will need to calculate in this order that so it's the way I have designed the transition. I could have designed it in the forward style as well, like from like this particular state needs things from the previous row. I can also design it that way. Just because I've written it in this way, I will also show one implementation in this fashion that you can change the loop orders if you want to. Okay, so sorry, we are going row major first. Am I audible and is the screen visible? Yeah. Okay. This is the looping part. Okay. So now if I is equal to n, then we are done, right? And we are also given some x that we want to find the value of at some x, right? So if I is equal to n, so if so in that case some base case values need to be filled in the DP array. So if I can say sum is equal to x, then my DP of I comma x is going to be equal to I comma sum is going to be equal to 1. Like there is one way in which I can form sum x, or else my DP of I comma sum is equal to 0. There is no way further that I can make the sum equal to x, right? This is some sort of base case. Remember this quick rule that in counting problems, generally the base case are 0 or 1. The count like min max problems, it's the opposite one, like minus infinity plus infinity and so on. If I is equal to n, so this is the base case, or else I will just quickly find out the value using next row's prefix sum. So I can create a separate array prefix sum, but anyways we don't need the values of this row anymore. So I will be doing it in place. So what I would be doing is I would be calculating the prefix sum in this place itself. So I would be just doing sum equal to 1, sum is less than equal to 5,000, sum plus plus. Okay, and dp of I comma sum. So note that when we are doing this particular loop, for the ith row, all the correct value has been calculated. So I will calculate this particular value over here as well, like this separate part using prefix sum of the next row. Okay, but before that we need to create the prefix sum. So for this particular row, I will also create the prefix sum so that before going to the previous row, I just have these values so that I can get the answers very fast, right? So dp of I comma sum is going to be equal to dp of I comma sum plus dp of I comma sum minus 1. So this is just creating a prefix sum, okay, on this particular row. Make sense? Now, of course, in the original problem, you might need to do with modulo and other things. I'm not handling that over here. It might overflow. In fact, it is not might, it will overflow in this particular implementation, but we can take care of mods here and there, okay? Now, with this, so basically, when we come to some ith row, we know that the next row has been transformed into its prefix sum format, right? So for this particular row, I can easily use the prefix sum of the next row. So for like let's say this particular sum. So over here for the ith value, I will take from the range li to ri, right? So the next sum plus li and sum plus ri, that's my range, okay? Int low is equal to sum plus li, l of I, okay? And integer high is equal to sum plus r of I, okay? Now high is equal to min of high comma 5000, because anyways we cannot go beyond 5000, right? And if low is greater than equal to 5000, then sorry, if it's greater than 5000, in fact it's not possible, okay? So the number of ways at this particular state is going to be equal to 0. Make sense? Or else it's going to be some prefix sum that is nothing but dp of I comma sum is equal to dp of I comma, let's say, high minus dp of I comma low minus 1. Now note that I'm not like checking something over here whether it's negative or not, because in the original problem everything is positive, like li is positive. I think I've written that, okay? So every constraint is almost always positive, that is given. You can also, like, if it's not positive, then you can take this as like modulo in place and check whether low minus 1 is becoming less than 0. So in that case, make it 0 or else. So I can write it something like this. If low is greater than 0, then use low minus 1 or else use 0. And with that done, we now have the correct value at dp of I. That's it. And then when this loop ends, we know the correct value for this particular row, calculate a prefix sum, and then go to the previous row, right? This is how you can do this. Now with this done, how do we know the answer? What is the answer now? Can somebody quickly tell me that? That's a bit wrong. That was correct, but in this code it will be wrong. No, I think so. Since we are okay, so since we are drawing the prefix sum from front to back, it will be correct. Okay. Yeah, that's okay. So this is going to be dp of 0, 0. So make sure that when you are doing the prefix sum, if you suppose had some other state as the solution, make sure that it's not affected by this prefix sum. That's what I wanted to have a check. So you could have implemented this prefix sum in the back in the suffix manner as well if you wanted. Okay. So in that case, you had to check this correctly, but in this case, it will work. Yeah, this will work. Okay. Is this clear to all? Like, this is how you help. This is how the iterative implementation helps at times, because it is way easier to write prefix sums over here in this panel, right? Also, sometimes, like, you can even implement this recursively if you want to. Just create another recursion which gives you the what do we need to check? Exactly. Okay, so what I'm saying is, let's say this particular last loop deforms the layer with a prefix sum, right? A particular layer's dp value with a prefix sum. So let's say you need the 0th layer's prefix sum, like some particular some index's value, but that might have got changed by this prefix sum, right? In this loop, because that's happening at the 0th row as well. So in that case, when you're using some prefix sum, make sure that you check that you're not taking the sum of things but the actual value. Okay, that's it. Okay, So this all is like the advantage of using iterative implementation. Like sometimes it helps with these kind of like quick prefix some codes. Also, you could have solved this using recursive as well. How? Very simple. Just define another DP. Like let's say